All right, today we're going on a bit of a wild ride. We're going to start with a tool so simple it's basically just an arrow, and we're going to follow that idea all the way to the absolute bleeding edge of physics, to a theory that tries to explain, well, everything in existence. So you ready? Let's follow the arrow. So here's the big question we're tackling today. How can something as basic as an arrow describe the ridiculously complex workings of our universe? And, maybe more importantly, what happens when that simple tool just isn't enough? What kinds of mysteries are lurking just beyond what it can explain?
To even begin to answer that, we first have to get a handle on the fundamental language physicists use to talk about reality itself. So let's start with the universe's building blocks.
And that language is built on this thing right here, the Euclidean vector. Now, don't let the name scare you. You can just think of it as an arrow. It's a really beautifully simple concept. It's just an object that has two key properties: a length, which we call its magnitude, and a direction it's pointing in. Seriously, that's it. The whole concept is just so intuitive. A vector is basically what you need to get from point A to point B. And the name itself kind of gives it away. The Latin word vector literally means carrier. It's the thing that carries you from your starting point to your destination. And that simple idea, carrying something from A to B, it's so incredibly powerful that vectors have become the fundamental language of physics. They're not just some tool, they are literally the way we write the rules of the universe.
And just look at what these arrows can do. They can describe the velocity of a planet whipping through space, the force of gravity holding it in orbit, the acceleration of a race car, and even those invisible electric and magnetic fields that power our entire modern world. It's an unbelievably versatile and powerful language.
But, every language has its limits. Every tool has a point where it just can't build any higher. So now, let's explore those boundaries, the exact point where our simple, trusty arrows start to fall short.
So after all that, you just have to ask, right? What can't these powerful arrows describe? Where does this elegant language just fall silent? This is where things get really, really interesting.
Well, they fall silent when we come face to face with the biggest questions out there. Like, why does time only flow forward? Or how does supermassive black holes even form? Why is the sun's corona millions of degrees hotter than its surface? And how in the world can we describe the pure chaos of turbulence? I mean, these are the huge, profound mysteries where our vector-based physics just doesn't have the answers. To solve these problems that live at this weird intersection of the very, very large, like gravity, and the very, very small, like quantum mechanics, physicists realized they needed a completely new language. So they set out on one of the most ambitious quests in all of science, the search for a single theory of everything. This has been the holy grail of physics ever since Einstein. The first massive leap forward was something called string theory, and it proposed this really radical new idea. What if the most fundamental bits of our universe aren't little points, but are instead tiny one-dimensional vibrating strings? The idea is that different vibrations of the very same string would just appear to us as different particles: an electron, a photon, a quark, the whole shebang. But as mind-blowing as string theory was, it wasn't the final word. A new idea started to bubble up, one that suggested all those different versions of string theory were actually just pieces of a much bigger and honestly much stranger puzzle. A theory that hints at a universe far, far beyond anything we can perceive. How much stranger, you ask? Well, get this. This theory doesn't take place in our familiar 3 spatial dimensions or even the 4 dimensions of spacetime. Nope. It requires 11. 10 dimensions of space and 1 of time. 11. Okay, so where are these other 7 dimensions? Well, the theory suggests they could be compactified. That means they're curled up so incredibly tight that they're completely invisible to us. Think about a garden hose. If you're looking at it from really far away, it just looks like a one-dimensional line. But when you get up close, you see it has a second dimension, right? Its circumference. These extra dimensions could be just like that, but on an impossibly tiny scale. And in this 11-dimensional space, we're not just talking about strings anymore. The theory introduces these things called branes, which is just short for membranes. So a point is a 0 brane, a string is a 1 brane, but you could also have 2 branes, 5 branes, you name it. These are basically higher dimensional surfaces that exist inside this much larger reality. So how did all these wild ideas, extra dimensions, vibrating strings, these branes, how did they manage to unify a completely fractured field and solve a major crisis in physics?
So back in the early 90s, things were kind of a mess. Instead of one theory of everything, string theorists had come up with 5. And they all seemed mathematically solid, but they all described different universes. It really looked like the whole project was a failure. Then, in 1995, a physicist named Edward Witten stood up at a conference and changed everything. Witten proposed this absolutely breathtaking idea. He said, what if the 5 competing string theories, and even this other theory called supergravity, what if they aren't competitors at all? What if they're just different ways of looking at the same single underlying theory? An 11-dimensional theory he decided to call M theory. It's like 5 people describing an elephant from different angles. One sees a trunk, another a leg, another a tail, but they're all looking at the exact same animal. This revelation was so huge, it was dubbed the second superstring revolution, and it totally unified the field. But it also left us with this beautiful, tantalizing mystery right at the heart of it all. The mystery of that M. And this is pretty much where we stand today. M theory holds this incredible promise of being the holy grail of physics, a true theory of everything, a single framework that unites all forces of nature. But here's the problem. For now, it's a purely mathematical idea. We have no way to actually test it, no experiment we can run that can prove it's the correct description of our reality.
Which brings us to the final question, and it's a question that just perfectly captures the current state of this grand quest. After all of this, what does that M in M theory actually stand for?
Well, the answer comes from Witten himself. He said the M could stand for magic, mystery, or membrane, depending on your taste. He figures the true meaning will only become clear when we finally understand the theory on a much deeper level. And that's just the perfect place to end, right on the frontier of knowledge, where science still feels a little bit like magic, and the greatest mysteries of the universe are still out there, just waiting to be solved.